Okay, so today we're going to start talking about gas movement. How do gas particles move? Well, they spontaneously, meaning sort of on their own, they have a tendency to move in a particular direction. And what we mean there is, if we look at a model here, if I have an area of high concentration of this red gas and an area of high concentration of this blue gas, and I take away the divider between them, what are they going to do? They're going to naturally mix with each other. And we're going to go from high concentration of red over here to those red particles are going to naturally move and migrate into the rest of the box. So they're going to the area of low concentration until eventually, after a minute or so, it's going to be a very even distribution of the red particles, and the same for the blue throughout the box. So we can say that gas particles spontaneously, and again, that means on their own, move from areas of high concentration to areas of low concentration. And then what we call this when gases mix, like what you just saw, this is called diffusion. So diffusion is the process of a gas spreading like throughout the room and mixing with other gases. So you saw that here in our little model. If I reset the divider here, they're going to naturally mix with each other as soon as I remove that divider, right? So that is called diffusion. So you could say that the red guys diffused across the room or across the box, across the container, and mixed with the little blue guys. And the same for the little blue guys, right? They're diffusing, they're mixing, they're spreading out. This happens naturally, and it happens naturally because gases will fill their container, right? They'll bounce around until something stops them, and then they'll bounce in the other direction until something stops them there. And the motion is pretty random, right? So that's called diffusion. There's also something called effusion or effusion, and that is a gas escaping from its container. So if you think about like a nail hole in a car tire, the gas particles are bouncing around inside of that car tire, and eventually, a good number of them are going to escape, and you're going to have a flat tire, right? That's called effusion. Now, both diffusion and effusion are governed by what's called Graham's law. And in Graham's law, you have this V. It doesn't stand for volume in this case. It's a lowercase v. It stands for velocity, like how fast the particles are moving. And then the M here stands for molar mass, as in the number from the periodic table. Now, if you'll notice, we have velocity of A, which just means we're comparing two gases. Gas A, its velocity will go on the top of the equation, but its molar mass over here inside of the radical sign, inside of the square root sign, its molar mass goes on the bottom. And the reason that its velocity is on top on one side and on the bottom on the other is because velocity is inversely related to molar mass. Now here's what I mean by that. If I go back to our we'll reset the divider, right? Let's look at them separately. Notice I've set the masses and the sizes of the particles differently. So the blue are much smaller, okay? The blue have a mass of 10 AMU, so that'd be about the size of neon atoms. And the red are 32 AMU, so that would be like an oxygen molecule or something else, much larger, right? Quite a bit larger than neon. And the radius, of course, would be larger too for the bigger, heavier, molecule. And what you'll notice is they're both at the same temperature. They're both in the same container. They're both in the same room, which means they're at the same temperature. You should notice here that the blue, on average, not every particle, but on average, the blue are moving faster than the red, right? So they're smaller. So at a given temperature, you would expect a smaller, lighter particle to move faster than a bigger, heavier one. That's very important to understand. Now, again, temperature is an average of the kinetic energy of particles. So is every red one moving slowly? No. Is every blue one moving quickly? No. But on average, the blue ones are moving much faster than the red ones because they are much smaller. That's an inverse relationship between mass and velocity. So we can use Graham's law to predict how fast a gas will diffuse or diffuse. So let's take a look at an example problem. We're basically just going to be learning how to utilize this little equation, okay? An unknown gas diffuses 1.5 times faster than SO2. What is its molar mass? All right, so we're going to set up our little fraction here, and we're going to set it equal to another fraction that's inside of a square root sign. And we're just going to assign our substances. In this case, we've got SO2, and then we have an unknown gas, right? And one of them we're going to call A, and the other one we're going to call B. And it doesn't really matter too much which one we assign to be which. But my unknown molar mass is what I'm looking for. I'm looking for the unknown molar mass, or the molar mass of the unknown gas. So the way I'm going to do this problem is I'm going to solve for the molar mass of what I will call gas B. That's my unknown. It goes on top. And then the molar mass of the other gas, gas A, is going to be SO2. So I would just go to the periodic table. Sulfur is 32.06. 2 oxygens would be another 16 times 2, so that's another 32. So we're looking at a total of 64.06 AMU. And again, just to be clear, we're calling that gas A, and that is SO2. And then the X, the unknown, is of course our unknown, right? Well, that means on the left, I have to put the velocity of the SO2 on top, because if SO2 is gas A, its velocity goes on top. So if I look at this, the problem says the unknown gas diffuses 1.5 times faster than SO2. So what that means is my velocity, we don't have to express this in miles per hour or meters per second. We're just going to say, we're just going to talk about relative velocities. And if the unknown is 1.5 times faster, then I'm going to give it the velocity 1.5. And apparently that's going to go on the bottom because its molar mass, which is X, is on top. And then the SO2, which is the slower gas, would be 1, because if you look at the statement, the unknown is 1.5 times faster than SO2. So 1.5 would be the relative velocity of the unknown, and 1 would be the SO2. And now we just have to solve for X, right? So if X is in the radical, it's in the square root sign, then we need to square it to get rid of that square root sign. So we've got to square this side, but we can't just square one side, we've got to square them both, right? So I'm going to get out my calculator, and I'm going to say in parentheses here, I'm going to have 1 on top, I'm going to have 1.5 on the bottom, and then I'm going to square this, and it gives me 0.4 repeating. So that's what all this on the left equals. Okay, so we have 0.44 4, and I can just say repeating, equals, and I got rid of the square root sign, so now it's just x over 64, or 64.06. And so now if I want to get x by itself, I just have to multiply both sides by 64. Oops. 64.06 AMU. Okay, and that cancels my 64.6 on the right. And now I have x by itself. So x will be equal to 0.44 repeating times 64.06. So I'm just going on the calculator. I'm just going to go down. I'm going to hit answer. And then I'm going to say times 64.06. And I get 28.47. So I'm just going to call that 28 because it looks like I only need 2 sig figs. So 28 AMU is the molar mass of my unknown gas. Okay. Go ahead and try the next two on your own. We will discuss those in class. The third one we'll do together. It's a little bit more challenging than the last one. You can try it if you want to, but really I want you to try the second, third examples and bring those to class with your attempts.